Again, thank you for coming, and thank you to our speakers who are here and are going to speak today, especially to Dr. Vega for coming all the way from Texas to speak to us. Thank you to Vanda Lewis, who's in the back, getting everybody to sign in and helping us out with lunch today. Tim Barefoot for videotaping and for our discussions and getting this all set up. At the end of all of this, I'm going to compile the presentations together. I'm going to put a summary together, and we'll make a booklet like the one that you picked up on the way in. And if you gave me your email address, I'll send it to you, or I may ask you for a mailing address. I'll send it to you. It might take me about a month or so to get it together. But my end goal is to go ahead and have some sort of a report that you all can take away with this, so you know what was said, what was done, and perhaps where you're interested in going from here. Are you focusing on females? Are you focusing on males? Are you going with genetically superior fish in order to possibly ensure more survival? What does it look like genetically speaking? Again, similar to safeguarding, what's the impact on wild stocks? And then would stocking impede existing management measures? Lauren, migration pattern of southern flounder in North Carolina. Does the demand justify stocking? The demand meaning public demand for the consumption and demand by commercial and recreational fishermen. How do we address the conflict between commercial netting and any sort of commercial fishing for flounder and stocking? Are there lessons from other states? We know there's several other states that are doing stock enhancement, and Dr. Vega will be speaking from the Texas perspective today. How do the results and the cost compare to traditional management? What marine fisheries is doing right now? And then is there simply public support in North Carolina for stocking? Again, the unknowns from the 1998 workshop. So there's a lot of unknowns that came out of 1998, lots of recommendations. So today, what I'd like to do is, as we hear from the presenters, to identify what do we know, what have we answered, and what's still out there in order to help us make the decision of whether or not, again, stock enhancement is right for North Carolina, would it have an impact, is it doable, and should there be any steps forward. So, again, goals for this workshop, what questions have been left over? Are there new questions surrounding stock enhancement? And is there enough available information to make the decision whether to move forward or not with stock enhancement? Okay, so I'd like to welcome Dr. John Miller from North Carolina State University. He is Professor Emeritus now. As I was telling him, I couldn't actually find him. I was looking in the past before he came to the meeting. So he was listed somewhere on the website. But I've asked John to kind of give us an idea about stock enhancement. He just wrote a chapter in a new book that Dr. Daniels put out on stock enhancement of flatfish southern and summer flounder. So I thought he'd give us a good introduction to stock enhancement and how it is relevant to
Okay. What I want to do today is to present the case for the more proactive management option of stocking southern flounder. No one can guarantee success, but now there's ample evidence that stocking works elsewhere and could work here. And that's what I'd like to present. Rearing southern flounder is no longer an obstacle, and there already exists adequate productive capacity in the state of North Carolina, both state and private hatcheries, to stock a meaningful number than was in 1998. So why consider stocking southern flounder? Current management is not working. According to the DMF, and this was in 2005, so this might have changed, the population is only 5% of what it was formerly. Stocking works elsewhere, for sure. And stocking could likely work in North Carolina. I want to spend most of my time with item 3, but in brief, much progress in the field of stock enhancement has been made in the last couple of decades. And it's clear that some additional steps are needed to ensure the future of southern flounder in North Carolina. The Japanese are now stocking 70 species of marine animals and plants in their waters. Half of them are fish. And of the 17 heavily exploited fish, and they really exploit their fish over there, The three which are holding their own against the increasing fishing pressure, all are stocked. The others are declining like most of ours. One of these species is Japanese flounder, which belongs to the same genus as our southern flounder. So a lot can be learned from them. Japanese flounder is also stocked in Russia and China. Turbot, which is another flatfish, is stocked successfully in Denmark, Spain, and Turkey. And, as you'll hear later, southern flounder is stocked in Texas. Many other species of roundfish, not flatfish, are stocked successfully in the U.S. and elsewhere. And it's become clear that Mother Nature is unable to keep up with the increasing pressure on nearly all the stocks, and they need help. Rationale for stocking are several. There are many objectives. The most common is number one, stock enhancement, when recruitment is the bottleneck. There's not enough babies to replenish the stock. Second is restocking, where the spawning stock biomass has been depleted and needs to be rebuilt. The third is to provide more catchable fish with no intention of increasing the stock. They just pollute the tank. Ecological stocking could be to restore community structure or to carry out experiments to determine carrying capacity, study species interactions, and so on. Fifth, a new fishery, for example, was established in Tokyo Bay by stocking older juveniles that fed on the goby population, the little fish population that lived there. The food resources for the younger fish were not there. So they established a new fishery by stocking older juveniles that could feed on the gobies, and now it's an extremely successful fishery. Stocking southern flounder in North Carolina would be for reasons 1 and 5 and maybe 6. There are several reasons to think stocking southern flounder in our sounds and rivers would substantially increase the availability of these fish. The estuaries are below the carrying capacity, at least there's evidence for that. Recruitment is limited by colonization, not by the spawning stock, as you'll see in a minute. Year class is not limited by the stock biomass. So increasing the number of adults will not increase the number of juveniles, at least in general. And there's much underutilized nursery area in North Carolina, at least I believe. Anyway, these are the main reasons or subjects for the rest of my talk. Estuaries below carrying capacity. What follows is the evidence that our estuaries could support stocked flounder. Next. In North Carolina, lives the green fish. Next. North Carolina Division of Marine Fisheries has conducted spring surveys in May and June in 105 of these nursery areas for 23 years, at least when we wrote this paper. And those numbers would provide the first index of year class strength or recruitment strength is the subject of our analysis. Anyway, it shows that these nursery areas are quite variably colonized from year to year. And it's the variation in the distribution among nurseries and the interannual variation in year class strength, up and down, one year, next year, that provide evidence that stocked fish would succeed. Next slide. The year-to-year variability and overall abundance in these nursery areas is about an order of magnitude, about a factor of 10, actually 8. This means that these nurseries are capable of supporting at least the maximum number of juveniles observed in the vesting years. In this case, it's 1966 is the data that we looked at. And depending on what limited the number in 1966, it could be more, a lot more, we'll see. When we looked at the initial distribution of southern flounder and the juveniles, in particular nurseries over 23 years of data that we analyzed, the numbers were quite variable, about 20-fold among these nurseries. Most of the southern flounder larvae end up in bays and lower reaches of Pamlico and New Zealand. Numbers were generally lower along the barrier islands, and reflecting the preference of southern flounder for the low salinity waters. But much of the low salinity water, the upper reaches of the rivers, and particularly Albemarle Sound, was not sampled in these surveys, which were designed to estimate shrimp abundance. So we couldn't really cover the whole state. Next slide. When we look at the individual year classes, we see southern flounder abundance at age 1. That's the green dots, 1 year after they leave the nurseries. And even age 2 is remarkably well correlated with the numbers in the juvenile surveys, the younger the year, the YOY year, the heavy black line. This clearly means that most of the interannual variability in abundance and recruitment is generated before the southern flounder get to the nurseries. And that pattern is only dampened 1 and possibly even 2 years later. But the main conclusion from these data is that there's no evidence for density-dependent mortality. That would be where even the strongest year classes would result in lower numbers, percentage-wise, the following year. They track very well for even 3 years. So they don't, even the strongest year classes, exceed the carrying capacity of the nursery system, which would be evidence of that higher mortality. Next one. Second reason to believe stocking would work is recruitment is limited by colonization, and this is really an interesting new finding. That is, the numbers of larvae or juveniles that reach the nursery areas. Once in the nursery areas, both growth and survival is high. More important, field experiments, where we put fish, juvenile flounder, southern flounder in cages up to 10 times the abundance that we see in the nursery area naturally, showed no evidence of suppressed growth. So clearly the system is capable of supporting more juvenile flounder than what exists now. Flounder spawn a few tens of kilometers off the coast in wintertime. They migrate to the narrow cracks in the inlets or in the barrier islands, and then across the bays and sounds to their nursery areas, which are below salinity. They don't have the strength to swim across the continental shelf, even a few miles here to, let's say, Oak Inlet. I scale that migration, and it's equivalent to you or I swimming around the planet in 30 days. So they're clearly at the mercy of currents, which transport them. They're not swimming there themselves. But not only must the larvae reach those narrow cracks, they've got to get through even stronger currents in the inlets, and then go across the sound. But after successful entry into and retention into the sounds, and they have a big risk of being washed back out if the inlets aren't behaving the way they should. The larvae and early juveniles are transported across the sound into these medium salinity creeks. Remember where most of them showed down the river. A process that takes about another month. So when they get to the nursery areas, they're about 2 months old and maybe about 1 inch in length. The peak abundance in those nursery areas is in May, when the Division of Marine Fisheries conducts these surveys, and possibly June. So very clearly, the process of getting to the nursery areas is quite hazardous, considering the currents that are much stronger than they can stem. And they're subject to winds and to pressure-driven forces that vary quite a bit from year to year. So those considerations led us to examine the possible relationship between winds and river discharge and year class strength. That's what we found. What we found with the cluster analysis, this is a statistician at NC State, committee was that the catches could be grouped into 7 clusters that behaved similarly from those 105 sampling stations. That showing very similar patterns of abundance. The inset there shows the catches in the 4 main clusters. The other 3 clusters either had too few fish or too few stations, so weren't considered in our analysis. The colors for the clusters are the same as the colors of the dots on the map. Cluster 1, those dark blue dots down here, near the outer banks, were low in numbers because they are high salinity, and southern flounder are low salinity species. The others had fairly similar patterns, differed mainly in overall abundance. Remember 1956 was the real good one. But it's clear again that most of the larvae ended up in the lower to middle reaches of the rivers, the red and the light blue dots. The next most abundantly colonized nursery areas, the green dots, are low salinity creeks and the uppermost nurseries in the Pamlico River. Next. What we found is very interesting. The colonization pattern was clearly related to wind and the river discharge in the 3 main classes, that is, most of the fish. Also, we could explain most of the interannual variation, year-to-year variation, in overall abundance with the model that we built. We had a physical oceanographer working with us at the time. So variation in year class strength in southern flounder, as evidenced by the numbers in the nursery areas, is clearly a colonization process. It just depends on how many get there, not how many adults were spawned. To recap, our statistical analysis disclosed some mechanistic relationships between meteorological factors, wind, rain, etc., and the juvenile abundance and pattern. The model we developed could explain up to 83% of the variability from year to year in these juvenile numbers. I'll spare you the details of the model, I'm not sure I understand myself. But to suffice it to say, the links make sense. That is, the winds that blow one way, the surface waters, the bottom waters go the other way, and that's the way the fish go. So they're riding the bottom currents up to their nursery areas. Our findings have been published in peer-reviewed literature, and if you're interested in it, I've got some copies of reprints that you can have. Next one. Most management models include a stock recruitment relationship, where simply the more spawning stock, the more recruits. That model was developed for salmon in the Pacific Northwest, and we've been trying for years to make it fit other species. And that's in fact, that's the basis for most of our management, is to increase the spawning stock biomass, and the principle is that should yield better recruitment. Well, that relationship is the center of most management strategies to increase the spawning stock biomass. However, that model doesn't take into account the variability in environment that determines the success of any reproductive method. That's why you get varying numbers of recruits from the same spawning stock. These numbers are fairly uncertain, but that's pretty clear. In fact, there are very few cases where the relationship holds for marine fish species. It works in salmon, but you remember the salmon life cycle is where the adults don't even have larval stages. They spawn in rivers, and the larvae are protected and grow in these rivers until they grow up and swim out into the ocean. So they're not exposed to the kind of variability that these southern flounder larvae are, that are only about that long. Southern flounder is a case in point, and perhaps to be expected that that relationship wouldn't work, considering all the environmental variability that the larvae are exposed to, making that long transport between the continental shelf and the inlets and the nursery areas. I'm afraid that we marine biologists, and I have to take Institute have been guilty of trying to make the biology of fish fit our mathematical models rather than the reverse. That's being recognized by lots of individuals. Recall the pattern of young year abundance, that's the black line, that shows approximately the 8-fold variation in abundance in the nurseries. Now look at the pattern of the abundance of the spawners. It doesn't fit. Spawning stock biomass of southern flounder varies about 2-fold, or varied over a period of time when we look. And it doesn't vary nearly enough to account for the 8 to 20-fold variation in numbers of water. If you remember the pattern of variation in recruitment, it's not even the same either. Remember 1966 was the largest recruitment year that we had. So it would seem in the case of southern flounder and probably other species that spawn offshore, like southern flounder, spot, program, well, we don't know, we haven't analyzed those data, that must reach these inshore nurseries after spawning offshore. Trying to manage the weather would probably be easier than trying to manage the fish. The fourth reason for thinking stock enhancement of southern flounder would work is the large amount of underutilized or unutilized nursery areas. Besides being under-colonized, those are some of the numbers that we see in the nurseries that were sampled. There's quite a bit of low salinity estuary area in North Carolina that appears to be uncolonized, yet suitable. We don't know this. We won't know this until we put southern flounder in there. Next one. We found that the majority of flounder in juveniles in any given year in this system was at the mouths of Pamlico and Neuse rivers. Those were the better colonized nurseries. It's likely that those nursery areas are at the upstream end of the current regime, which transports larvae from the juveniles from the inlets. That is, there's a lot of area above, low salinity area, that the larvae can't get to because the currents don't take them there, or won't take them there. That is, even though there are low salinity bays upstream, fish can't get to colonize. The same applies to Albemarle Sound in spades. Winds that generate currents that would transport larvae along the bottom into Albemarle Sound also blow the Sound surface waters towards the east. And that sets up a hydrostatic pressure barrier. Yes?
When you're mentioning underutilized nursery areas,
Yeah.
and factoring in their currents, at what point coming inland or salinity starts playing a part?
Salinity plays a part. River discharge plays a part. That's why our model had both the winds, which generated the currents, and the river discharge. In years when the river was discharging too much, it actually kept the larvae from some of these nursery areas. But the point I'm making is that there's a lot of area upstream from the main colonization points, and particularly in Albemarle Sound, that is very difficult, if not impossible, to colonize. Yet it has low salinity. It seems like it would support the fish. We can discuss this a little bit further. It's well known that flounder will grow and survive in Albemarle Sound. I've taught them fishing for bass. It's reported that a large forage base exists there too, that there are a lot of baby fish on which they could feed. That's not for sure, but it seems like it's the case. And so Albemarle Sound, if stocked with southern flounder, could represent a huge addition to the flounder stocks in North Carolina. If a decision is made to start dry stocking, some essential safeguards, of course, have to be in place. Fish that are stocked must be screened for diseases. The North Carolina State University Vet School could easily develop a protocol for screening fish for common diseases. Second, both the hatchery and wild fish should be genetically profiled to be able to detect any genetic dilution by the stocked fish. Third, there should be a follow-up plan in place to find out whether or not the stocking is working. Fortunately, most hatchery reared fish are marked naturally by dark spots underneath their blind spot. So all you have to do is pick them up and turn them over, you can tell whether they came from the hatchery or whether they're wild fish. That makes it a lot easier than having to genetically profile or to tag them with small tags. Fourth, stockfish comprise up to 74% of the commercial catch. In the case of red sea bream in Japan, it works. But the percentage is necessary, that we would say is necessary, to judge the stocking a success is something that needs to be determined. Fifth, by involving the fishermen at the outset, a sense of ownership is established in the stock. This has been shown several places, Texas, Japan, and others. The fishermen feel like it's their stock, not some common resource, and it's been shown that they're less likely to take too many fish or undersized fish. Finally, and perhaps most important, the bycatch of juvenile flounder must be reduced. Nearly 80% of the shrimp is harvested in North Carolina comes from the Sounds. The bycatch, which could be as high as 18 pounds of fin fish per pound of shrimp, is comprised of 67% flatfish. That is 73% southern flounder and 26% summer flounder, according to a Sea Grant-sponsored research report. Unfortunately, the inshore shrimping grounds in North Carolina include the summer and fall migration routes of these juvenile fish. Texas, like most states in the southeast, has banned most of the inshore netting, but no population can stand to have their juveniles destroyed by bycatch. We know that. Next one. Well, many things have been learned in the course of recent stock enhancement research. In Japan, the optimal stocking size has been determined to be about 3 inches. Smaller fish are cheaper to raise, but they don't survive as well. And bigger fish survive better, but they cost more for raise. The highest market return rate for Japanese flounder, that is the number of fish treated per the cost of the fish released, is about 3 inches. Likely that's different for different species, but maybe not so good. Or perhaps in some flounder it might be a little different. Returns from different stocking areas are different. We know that I've been working in Japan for several years to determine why some nursery areas yield a better return than others do. In general, releasing fish in relatively predator-free water is better, which our areas upstream are, and that incidentally would be another reason for concentrating on southern rather than summer flounder, which occupy the higher salinity, more predator occupied areas. The timing of release should be matched to the food resources, and at least tens to hundreds of thousands of fish should be released to have a significant effect. Stocking many fewer simply won't do, and the Japanese have shown, as have the people in Denmark. Finally, it's well known that hatchery reared fish are often subject to higher mortality rates than wild fish. Some prefectures in Japan hold fish in the field for a couple of weeks to acclimate to the wild food and predators from the hatchery. In Texas, juvenile red drums are held in rearing ponds for a few weeks before release to help them transition to the wild food. And structure can be provided to help them learn to avoid predation. Next. The time's passed when we can expect Mother Nature to provide the resources for an ever-increasing population. It's only a question of how we manipulate nature, not whether we do it. Stocking is only one proven way of increasing or protecting fish populations, and should be considered to be another management tool, not a replacement for conventional management. We know it works. Given advances in rearing technology, which we'll hear about today, a relatively cheap and secure way to improve stocks available for both sports and commercial fishing exists. North Carolina estuaries formerly supported at least 20 times the present stock. Clearly, the support capacity is there. If managers would take steps to reduce bycatch and support responsible stock management, it's possible we could see sustainable flounder fishing at even higher levels than ever before. We would like to thank the National Fisheries Service and Sea Grant for the financial support. We certainly